Let's discuss about the haloalkanes. As you know, haloalkanes are halogen derivatives of alkanes. Halogen derivatives of alkanes means alkanes in which one hydrogen has been replaced by a halogen. So alkanes have a general formula CnH2n plus 2. So what we are doing, we are replacing one hydrogen of alkanes by X. So it becomes CnH2n plus 1X. This is the general formula for haloalkanes. And these haloalkanes have a common name also called alkyl halides. Alkyl halides. So CnH2n plus 1, this is called alkyl group and X stands for halide ion. So first of all, we'll discuss about the nomenclature of haloalkanes. Now, the common name is alkyl halide. Common name is alkyl halide. So you have to identify the alkyl group. You just count the total number of carbon atoms, identify the alkyl group, and then you write a suffix halide. For example, CH3, CH2, and the CH2Br. Now in this case, the total number of carbon equals to 3. So it's called propyl, and then we write a suffix bromide. So propyl bromide. Now in this case, the carbon to which the functional group is attached is called alpha carbon atom. Now in this case, all three carbon atoms are in a state chain with the alpha carbon at the number 1. So we write normal as a prefix. So it's called N-propyl bromide. Now in this case, the alpha carbon is attached to one other carbon. So this is called a primary alkyl halide 1 degree. So you can write 1 degree instead of writing the whole primary as a word. So you can write 1 degree. So this is N-propyl bromide and it is a primary alkyl halide. Now in IUPAC system, halogen comes as a prefix, always comes as a prefix. Halo to the parent hydrocarbon. To the parent hydrocarbon. So you have to just say hello to the parent hydrocarbon in the IUPAC system. And this halogen should get the minimum number in the longest continuous chain. For example, you are given CH3, CH2, and the CH2Br. Now in this case, your alpha carbon is at the end of the chain. We start numbering with this carbon only. So 1, 2, 3. So bromine position is number 1. So we write 1 bromopropane. Now we'll discuss some more examples like this. CH3, CH3, and the chlorine. Now in this case, we have total 3 carbons present. So again we write propyl and we write chloride as a suffix in the common system. Now in this case, your alpha carbon is attached to 2 other carbon. This is a 2 degree alkyl halide. But at the same time, in this case, this group is present. And whenever you have this type of group present, you write iso as a prefix. So iso always gets a preference over secondary, over tertiary, over primary. So its common name is isopropyl chloride. Now in the IUPAC system, you have to number the carbon atoms in such a way that alpha carbon should get the minimum number. So in this case, we have 3 carbons in the longest chain, 1, 2, 3, and the position of the chlorine is number 2. So the IUPAC name is 2-chloropropane. So remember, iso group is when 2 methyl groups are directly bonded to CH, and iso always gets a preference over 2 degree. Now next example is this. This is the next example. Now in this case, 4 carbons are present. So its common name is isobutyl chloride. Isobutyl chloride, because the iso group is present. So we write iso as a prefix. Now its IUPAC name is 1-chloro and 2-methyl propane. This is IUPAC name. So numbering starts with this carbon 1, 2, 3. This is also 1 degree alkyl halide. But remember, primary never comes as a prefix in the common system. So whenever you have a primary alkyl halide, you look for some other prefix like normal, iso, neo, like this. Now some more examples we'll discuss now. CH3, CH2, and the CHCl and the CH3. Now in this case again we have 4 carbons present, so we write butyl and then we write chloride. Now in this case the alpha carbon is attached to 2 other carbons, so this is 2 degree and we write sec as a prefix. Right? Now it's a IUPAC name, the longest chain has 4 carbon atoms present, 1, 2, 3, 4. So its name is 2-chlorobutane. 2-chlorobutane. I'll write 2 more examples. This is the next example. CH3, CCl, CH3 and CH3. Now its a common name is tertiary butyl chloride because the alpha carbon is attached to 3 other carbon atoms. It's a tertiary, 3 degree. Now its IUPAC name is 2-chloro-2-methyl propane. 2-chloro-2-methyl propane. Now we'll discuss one more example like this one, CH3, CCH3, CH3 and the CH2Cl. Now total carbon present in this example is 5, so we write it's a pentyl chloride. But in this case, it's a 1 degree alkyl halide, but 1 degree primary never comes as a prefix. Now in this example, you have a 4 degree carbon present, quaternary carbon present at the end of the chain. Then we write neo as a prefix. So to write neo as a prefix, minimum 5 carbons should be present in the given compound. Now its IUPAC name is this one. This is the longest chain, 1, 2, 3. So we write 1-chloro 2,2 dimethyl propane. This is the IUPAC name. Now next, if we have a double bond and the halogen both present, then the double bond should get the preference. My double bond should be given the minimum number. For example, this is a bond line structure. Now in this case, the double bond should be given the preference. So we start numbering from this side. 1, 2, 3, 4, 5. So its name is, IUPAC name is 4-chloro pent. There are 5 carbons and double bond at the number 2 position. So we write pent 2-ene. Now in this case, your beta carbon is doubly bonded. Like this is the alpha carbon, this is a beta carbon. And whenever you have a beta carbon doubly bonded, that class of compound is called allylic. So this class of compound is called allylic. So whenever you have a beta carbon sp2 hybridized, beta carbon doubly bonded, it's called allylic halide. So this class of compound is called allylic halide. One more example like this one, CH2 double bond CH and the CH2Cl. Now its a common name is allyl chloride. So its IUPAC name is 3-chloro prop 1-ene. So this is the IUPAC name of this example. So this is about the nomenclature. And one more example to discuss now. Suppose you are given this CH2 double bond CH and the Cl. This compound has a common name called vinyl chloride, and we use vinyl as a class of compound when the alpha carbon is doubly bonded. Now its IUPAC name is chloroethene. And this last example to discuss now, a double bond, like this is the example given to you. Now in this case, the double bond again gets a preference, so we start numbering from this side. 1, 2, 3, 4, 5. So the IUPAC name is 2-bromo, so we arrange all the prefixes alphabetically. 4-methyl, and then we write pent 2-ene. Now in this case, your alpha carbon is doubly bonded. So this class of compound is called a vinylic halide. Vinylic halide. Now next we'll discuss about the preparation of haloalkanes. And we have number of methods to prepare haloalkanes. So we'll discuss about the preparation of haloalkanes. Preparation of haloalkanes, and the first method A is direct halogenation of alkane. Direct halogenation of alkanes means we have to replace the hydrogen of the alkanes by halogen. So this is called the substitution, but as you know, alkanes are saturated hydrocarbons. This is abbreviation I'm using for hydrocarbons containing a non-polar, almost non-polar, strong CH bond. So this bond you can break only in the presence of light or high temperature or both. So this CH bond can be broken only in the presence of light. Any light you can write, UV light, sunlight, bright sunlight, diffuse sunlight, light or high temperature, or we sometimes write both. And the bond will break up homolytically, gives the radical. So the mechanism of halogenation of alkanes is a free radical mechanism. So whenever the reaction requires the presence of light, high temperature or electricity, it means the reaction is proceeding via radicals. And the converse is also true. If I write it's a free radical mechanism, it means it requires the presence of light or heat or both sometimes. Free radical mechanism. And for a given alkane, the reactivity of halogens follows the order that fluorine is the most reactive. So fluorine reactions with alkanes are explosive in nature. Then comes chlorine, then comes bromine, and the iodine reaction with alkanes are generally reversible. So I'll start with first example now. This is called methane. Now in case of methane, all four hydrogens are identical. They have the same chemical environment. So when you react this compound with chlorine in the presence of a light, and our aim is to replace only one H, so any one H you can replace because all four are identical. So in this case, one and only one product is obtained. This is called a chloromethane. Now, if you start with the ethane now, ethane contains 6 hydrogen atoms, but all 6 hydrogens have the same chemical surrounding. All 6 hydrogens are chemically same. So if I react this compound again with chlorine in the presence of sunlight, again any hydrogen you can replace. So one and only one product is obtained, and this is called a chloroethane. This is side product HCl. Now next example is of propane. Now in case of propane, these two hydrogens are identical because each methyl group is bonded to CH2. So we call these 6 hydrogens as set 1 because all these hydrogens are chemically identical and these two are different. So we call it set number 2. Now we have a choice. When I react this compound propane with chlorine in the presence of sunlight, or this is a light symbol, we write photon. And now we have a choice. Either I can replace one H from the set number 1 or I can replace H from the set 2. So the two products are possible. One is this, 1 chloropropane and the second one is 2-chloropropane. So in this case, since there were two different sets of hydrogen, so two products are obtained. So we can generalize the number of mono-halo products obtained. Number of mono-halo products formed, it depends on the number of different sets of hydrogens. Number of different sets of hydrogens. Now next question comes, ki how do you decide which one is the major one? So since it follows a radical mechanism, so the stability of the radicals you have to look into. The more stable the radical is, more the percentage of that product formed. So the ease of substitution or ease of replacement of hydrogen, ease of replacement of H means which hydrogen can easily be replaced. Replacing which hydrogen gives you the major product. Look at this. Ease of replacement of hydrogen follows the order 1 degree, 2 degree, 3 degree. Now since in this case, this hydrogen is 2 degree, when you replace the hydrogen from the 2 degree carbon, it gives the major product. So this is my major product and this is my minor product. So this way you have to decide. So two things you have to follow. One, how many products are obtained, that depends on the number of different sets of hydrogen. Then which one is the major one? Look at the stability. Ease of replacement of H follows the order primary, secondary and tertiary. Now this one example more. Now suppose you are given this. Now this is called isopentane. 2-methylbutane is the IUPAC name. Now in this case, we have 4 different sets of hydrogen. Now this is 2-methylbutane. Now this 2-methylbutane or isopentane has 4 different sets of hydrogens. If you look at this methyl group, bonded to CH. This CH3 is bonded to CH. This is also bonded to CH. So they both have the same environment. So this is set number 1. Now this CH3 is bonded to CH2, has a different environment. So it is a set number 2. This is set number 3. This is set number 4. So when you perform chlorination in the presence of light, will produce 4 products. And these are the 4 products. These are the 4 products obtained. This is number 1. When you replace hydrogen from the set number 1. This is second product. When we replace hydrogen from the set number 2. And this is third product. When you replace hydrogen from the set number 3. And this is a fourth product when we replace hydrogen from the set number 4. So 4 products are formed because there were 4 different sets of hydrogens. And out of these 4 products, this is the major one. Because you are replacing hydrogen of the 3 degree carbon atoms. This is 3 degree. So ease of replacement of hydrogen is 1 degree, 2 degree, 3 degree. The second method is the hydrohalogenation of alkenes. Hydrohalogenation of alkenes means the addition of HX, addition of H plus and X negative across the double bond. Now this is my double bond. So we are adding HX. This is called hydrohalogenation. So H plus ion is called electrophile. Is electron deficient, and X minus is called a nucleophile, electron rich. So this reaction takes place in the presence of dark, and H adds to one doubly bonded carbon and X adds to second doubly bonded carbon, and the product obtained is the haloalkane. Now if your alkane is symmetrical, in case of symmetrical alkene, add H positive to any carbon of the double bond. Any carbon of the double bond. And in case of unsymmetrical, alkene, H plus ion adds to the carbon which contains more number of hydrogens, more number of hydrogen atoms. This is called, if you remember, Markovnikov's rule. This is called Markovnikov's rule. Now we'll discuss some examples. Now first example is this. Now if you look at this is a symmetrical alkene, but2ene. So if you are reacting this compound with HCl, in dark you can add H positive to any carbon of the double bond. So this is my product. It's called 2-chlorobutane. Now if you are given this one now, CH3, this is called 2-methyl-but2ene, and we are reacting it with HBr. Again in dark, light should not be present. So it follows Markovnikov rule. H adds to this carbon and bromine adds to this carbon. So my product is 2-bromo-2-methyl-butane. One more example we can take. This is methyl cyclohexane. We are reacting it with HI. Now in this case, it's unsymmetrical alkene. So H adds to this carbon and I minus adds to this carbon. So my answer is this one. This is called 1-iodo 1-methyl cyclohexane. Now next is if we add HBr to alkenes in the presence of organic peroxide, then the addition takes place according to anti-Markovnikov rule. According to anti-Markovnikov rule. For example, this is propene and we are reacting with HBr in the presence of peroxide. Benzoyl peroxide can be used. So addition takes place according to anti-Markovnikov rule. So it gives a 1-bromopropane. One more example, CH2, CH double bond, CH2, and we are reacting it with HBr and peroxide. But remember, anti-Markovnikov takes place when the HBr and the peroxide both should be present together. If anyone is missing, you just request the Markovnikov. So my answer is this now. And remember, this anti-Markovnikov addition follows radical mechanism, but Markovnikov follows ionic mechanism. Now the next method to prepare haloalkane is from alcohol. From alcohols. Now if you look at the alcohols are represented by ROH, and our aim is to prepare RX. It means our aim is to replace the OH by X. And OH can be replaced only as a negative group. So negative can be replaced by negative. So this is called nucleophilic substitution. This is an example of a nucleophilic substitution. But replacement of OH is difficult because CO bond is stronger than carbon halogen bond. So the removal of OH from alcohol always requires the presence of some Lewis acid as a catalyst. Lewis acid is electron pair acceptor and helps in the removal of OH as OH minus. So there are a number of ways to replace OH by X. For example, we are reacting the alcohol with HCl. But in the presence of anhydrous ZnCl2 as a Lewis acid. HCl is not a very strong acid, so it does not give enough H plus ion. That's why we are using Lewis acid from outside in the form of anhydrous ZnCl2. So the loss of water takes place and it gives you RCl plus water. This is not an easy method because we are using two things here. One is the reagent hydrochloric acid, second the catalyst anhydrous ZnCl2. So our aim is we are looking for some reagent which can perform a dual role, means which can supply halogen as well as act as a Lewis acid. So we use phosphorus halides. For example, alcohol on reaction with PX5, where X can be chlorine or bromine, it forms RX. So OH has been replaced by X. And our side products are POX3 and the HX. So we can use phosphorus pentahalide. Phosphorus has a vacant d atomic orbital, so phosphorus can act as a Lewis acid also. And since PX bond is weaker, so it can easily supply X minus also. We can also use PX3, where X can be chlorine, bromine, and we prefer chlorine generally. So it forms RX, and my side product is a phosphorus acid H3PO3. We can also use with alcohol a sulfonyl chloride, sulfur oxychloride, thionyl chloride. Thio in organic stands for sulfur, in the presence of some base called pyridine. So we use pyridine as a base, and the role of the pyridine is to remove HCl from the right hand side. And since both the side products are gases, HCl is a gas, sulfur dioxide is a gas, so they escape into the atmosphere and they help in shifting the equilibrium in the forward direction. So we prefer SOCl2 over other reagents. So as a student, whenever you have to replace the OH by Cl, you always prefer SOCl2 or PCl5. I can write anything in my question. Now, two examples now. One is this, CH3, CHOH, CH3. We are reacting it with PCl5. So it gives you CH3, CHCl, and the CH3 as a major product. Right? This is a major product. So whenever you want to replace OH by Cl, you prefer SOCl2 or PCl5. Now, next example is this. So difficulty level is also increasing from example to example. So I'm using SOCl2. Now again, you should remember the role of the SOCl2 is to replace OH by Cl. So just look at the OH. Although it's a carboxylic acid group present, but there is a OH. So replace this OH by Cl. And side products, as you know, sulfur dioxide and the hydrogen chloride gas. This compound contains two OH groups. One OH group is directly bonded to benzene and the other OH group is on the side chain. Now the question comes, how do you decide whether we should replace both OH or one OH? If one OH, then which one? Now, any group directly bonded to benzene is always difficult to displace due to resonance, right? So this hydrogen chloride in the presence of anhydrous ZnCl2 will replace only the OH on the side chain. The OH group directly bonded to benzene remains unaffected. So these are the things you should remember. So only this OH can be replaced, not the OH directly bonded to benzene. Now the next method is number D. This is called halide exchange. So from the name itself, you can understand what is the meaning of this reaction, replacing one halogen by another halogen. Replacing one X by another X. But this method is mainly used to prepare fluoro and iodo compounds. Now first is fluoro compound. Fluoro compound. So in this case, what we do, we react the haloalkane where X can be chlorine or bromine with AgF, silver fluoride. It gives RF and the side product is AgX, either AgCl, which is white precipitate, can be removed. AgBr, pale yellow PPT, can be removed, so equilibrium can be shifted in the forward direction. So we have replaced the X by fluorine. Now this method is called a Swarts reaction. Swarts reaction. This is called Swarts reaction. We have other reagents also available. We have other reagents also available to replace chlorine or bromine by fluorine. For example, you can use Hg2F2. It's a mercurous fluoride. You can use cobalt fluoride. You can use antimony trifluoride. But whenever you have to write, you always prefer AgF. Reason? Because there is no subscript. So chances of mistakes are less. In Hg2F2, there are two subscripts. If you forget to write one subscript, you will get 0. So that's why, as a student, whenever you want to write the reagent, you always prefer AgF. I can write anything in my question. For example, this CH3CH2Br on reaction with AgF gives CH3CH2F, and my side product is AgBr. And we prefer this Hg2F2 when you want to replace more than one halogen by fluorine. For example, this 1,2 dibromoethane is being treated with Hg2F2, so it will form 1,2 difluoroethane. This is. Now the second is a iodo compound. So we prepare iodo compound by reacting the haloalkane. Again, X can be chlorine and bromine. Reacting with the sodium iodide in the presence of dry acetone. Dry means it's anhydrous, no water, no moisture. Dry acetone. It forms iodoalkane. So X has been replaced by iodine and our side product is NaX. So this reaction is called a Finkelstein reaction. Finkelstein reaction. So all named reactions have a specific reagent. You can't change anything. This is a Finkelstein. Now one example, suppose you are given CH3CH2Br and you are reacting it with the NaI in dry acetone. It gives iodoethane. So this is a Finkelstein reaction and very good method to prepare iodo compounds. Now we'll discuss two conversions now. Now question is convert propene into, the first is 1-fluoropropane and the second is 1-iodopropane. And both these conversions have the same concept. So our starting compound is propene, and always prefer the functional group on your right hand side. And our aim is to prepare 1-fluoropropane. This is 1-fluoro and this is 1-iodopropane. So basically we have to break the double bond by adding HF or HI, but you can't add HF according to anti-Markovnikov. You can't add HI according to anti-Markov. So the only reagent which you can add according to anti-Markovnikov is HBr. So you have no other option except to add HBr or bromine at the number 1 carbon. So we write HBr in the presence of peroxide, it gives me 1 bromopropane, and after this you follow Swartz selection. So as a student, I will always prefer AGF, or this is 1 iodopropane using NaI and dry acetone. So this is the way you have to perform the conversions. Propene into 1 fluoropropane and propene into 1 iodopropane. So this is all about the preparation of haloalkanes. Now we'll discuss about the physical properties of haloalkanes. Physical properties of haloalkanes. Now first of all, we'll discuss about the boiling points. And boiling point means the temperature at which the liquid changes into its vapor form. The temperature at which the vapor pressure is equal to the atmospheric pressure. Now, how much heat you have to supply to change the liquid into vapor, it depends on the intermolecular forces of attraction. So boiling points, so I'm using this abbreviation, it depends on the intermolecular forces of attraction. And in the organic compounds, we have mainly 3 types of intermolecular forces of attraction. Either you will have a H bonding, or you have a dipole-dipole, or you have the weakest dispersion forces, or you can write the van der Waals forces. Now, since haloalkanes are polar, haloalkanes are polar, right? This bond is polar in nature. X is negative, carbon is positive. So the intermolecular forces of attraction in haloalkanes are dipole-dipole attractions and are stronger than the dispersion forces in alkanes. Dispersion forces in alkanes. And that's why the haloalkanes have a higher boiling point than alkanes. Boiling point. So whenever you're moving from one homologous series to another, you look at the nature of the intermolecular forces of attraction, whether you have H bonding or dipole-dipole or the dispersion forces. But whenever you are moving down the homologous series in the same homologous series, then now down the homologous series, these points are same in all the homologous series. Down the homologous series, like we are moving from chloromethane, chloroethane, chloropropane, right? Down the homologous series, molecular mass increases. This is molecular mass. Increases. Then as a result, the surface area increases. And down the series, the dispersion forces dominates over other forces. So the dispersion forces also increases. And the boiling point also increases. So these are general points in all the function group homologous series. All these 3 points, 4 points, all these 4 points increases down the homologous series. That's why this chloropropane has a higher boiling point than chloroethane, has a higher boiling point than chloromethane. I think this point is clear to you. Now, next point, for the same haloalkane, this is the effect of branching on the boiling point. For the same haloalkane, as the branching increases, this is abbreviation, this is a sign we are using for increasing. As the branching increases, the molecule become more compact and tends to acquire spherical shape, tends to acquire a spherical shape. So as a result, the surface area decreases, dispersion forces decreases, and the boiling point decreases. So that's why this isopropyl chloride has a lower boiling point than the normal propyl chloride. The next point is for the same number of carbon atoms, for the same number of carbon atoms, as we move from fluorine to iodine, again the same points, molecular mass increases, surface area increases, dispersion forces increases, and the boiling point increases. So write this way in a compact form, in a short form. So our boiling point order is this: RF, RCl, RBr, and Ri. This is the order of increasing boiling point. The next point, for the same number of carbon atoms, for the same number of carbon and the same halogen, for the same number of carbon atoms and the same halogen, meaning you keep your halogen same, either chlorine or bromine or iodine, same X. As the number of X increases, again the same thing, molecular mass, surface area, dispersion forces, boiling point increases. That's why CH3Cl has the lowest boiling point, is a gas. Then comes CH2Cl2, then comes CHCl3 chloroform, then comes CCl4, and both these are liquids. So it proves that the boiling point increases. Now next point is the solubility. Now haloalkanes are, though polar in nature, but still they are immiscible in water. They are immiscible in water because they are incapable of forming hydrogen bonds with water. It's a simple reason, with water. But haloalkanes are miscible in organic solvents. They are soluble in organic solvents like benzene, carbon tetrachloride solvent, because the like interactions between the haloalkane and haloalkane are almost same as the solvent interaction, organic solvent and organic solvent. These interactions are almost same as the interaction between the haloalkanes and organic solvent. And the last point, their solubility in general decreases down the homologous series. In general, decreases down the homologous series. Homologous series. Now, next point is the reactivity of haloalkanes. This is a very, very important point, the reactivity of haloalkanes. Now, first thing, what is the meaning of reactivity of haloalkanes? Now, reactivity means how easily the X can be replaced as X minus. How easily the X halogen can be replaced as X negative, as a nucleophile. So the main reactions of haloalkanes are nucleophilic substitution reactions. Nucleophilic substitution reactions. Now, how easily the X can be replaced, it depends on the reactivity of haloalkanes is inversely proportional to the bond strength of the carbon X bond. So if the carbon halogen bond is weak, it means X can be easily replaceable, so more the reactivity. So if you look at the same alkyl group but different halogens like this one, fluorine, CH2Cl, chlorine, this is bromine, and this is iodine. Now if you see in all these, the carbon is same, sp3 hybridized, but the size of the halogen is changing from fluorine to iodine. Fluorine is from the second period of the periodic table using 2p orbital, chlorine is using 3p, 4p and the 5p. So the extent of overlapping decreases. So as we move from fluorine to iodine, the strength of the carbon halogen bond decreases. Therefore, the reactivity increases. As a result, iodine is easily replaceable. So we use the term that iodine can depart on its own very easily. It's a very good leaving group. Any group which can depart on its own. So leaving group ability increases in this order. Leaving group ability increases. So I minus is the best leaving group and F minus is the poorest leaving group. So the base strength So I minus is the best leaving group, but at the same time I minus is the weakest base. Now next is what are the different ways to replace X as X minus. Different ways to replace X negative by Nu negative, where Nu negative stands for the nucleophile. Now one possible way is this, the first way, that we are moving the X negative in number of steps. Now first way is we are replacing the X minus by Nu minus in a stepwise manner like this one. Like first we are breaking the carbon halogen bond. We are requesting the X to leave first. So this is called the bond breaking. And it results in the formation of a carbocation. So we are requesting the X minus to leave, right? And then we are requesting the incoming nucleophile to attack and form a bond with the positively charged carbon. So this is called bond formation. So reaction is actually taking place in two steps. So the first way is a two-step mechanism. Two-step mechanism. Now second possible way is that removal of X and the arrival of nucleophile takes place simultaneously. Means the bond breaking and the bond formation takes place simultaneously. Like this. This is my nucleophile and this is my haloalkane. So arrival of nucleophile and the departure of X negative. So bond formation between carbonyl nucleophile and the bond breaking CX takes place simultaneously, and this results in the formation of a transition state. Now in the transition state, the bonds are not completely formed and not completely broken, right? So carbon is bonded to half bonded to X and half bonded to nucleophile. And then it results in the formation of a final product. So these are the two possible ways to replace X as X negative. Now the question comes, how you decide? This is a one-step mechanism. One more point. This is called one-step mechanism, because bond formation and breaking takes place simultaneously. Now the question comes, how do you decide my haloalkane will follow which way? It's a two-step mechanism it will follow, or it will follow one-step mechanism. It depends on the structure of the parent alkane. Now in the two-step mechanism, the formation of this carbocation is the rate determining step. Means the rate of reaction depends how stable the carbocation is, how easily the carbocation is formed, how easily you are breaking the carbon-halogen bond. That's the rate determining step. And in this rate determining step, we have only one reactant molecule. We have only one reactant. So this reaction is called SN1 mechanism. SN1, because it's a unimolecular, you have only one reactant in the rate determining step, right? That's why one. One means unimolecular, N means nucleophilic, S means substitution. Unimolecular nucleophilic substitution. Now in the second mechanism, this is my rate determining step, and this rate determining step has two reactant molecules, nucleophile as well as my haloalkane. So in this case, the molecularity is 2. This is called bimolecular. So this is called SN2 mechanism. So how do you decide my molecule will undergo SN1 or SN2? It depends on the number of factors. Now, in SN1 and SN2, SN1 is a two-step mechanism. SN2 is a one-step mechanism. Bond formation and breaking takes place simultaneously. Bond formation and bond breaking takes place simultaneously. In SN1, the step 1 is bond breaking. Bond breaking, and the step 2 is bond formation. And in this case, the rate determining step is the carbocation formation. And my rate equation is this: rate depends only on the concentration of the haloalkanes, not on the nucleophile concentration. But in SN2, rate determining step is the formation of a transition state. So the rate equation is this: R equals to K. Rx, it also depends on the concentration of the nucleophile. Now in SN1 mechanism, the reactivity order of haloalkane is this. 3 degree is the most reactive because it gives a stable 3 degree carbocation, then 2 degree, and then 1 degree. So as the crowding increases at the alpha carbon, the reactivity towards SN1 increases. In this case, the nucleophile attacks at the alpha carbon from the back side, so the alpha carbon should be more and more exposed, alpha carbon should have less and less crowding. So the reactivity order in this case is 3 degree is the least reactive, 2 degree, and primary is the most reactive. And SN1 reaction is favored by polar solvents. Favored by polar solvents. And SN2 is favored by a non-polar solvents. Now we'll discuss some examples like in the given pair of compound, which one is more reactive towards a given type of reaction. For example, these are two columns given, and the first example is this. Out of these two, which one is more reactive towards SN1? This is tertiary butyl chloride, and this one is called a secondary butyl chloride, and our aim is to see about the SN1 reactivity. Now, this is more reactive because loss of chlorine gives a stable 3 degree carbocation. So simple answer. Now one more example. Out of these two, this is called allyl chloride and this is called isopropyl chloride. So which one is more reactive towards SN1? Again the answer is the first one, because the loss of chlorine gives allyl carbocation which is resonance stabilized. Allyl carbocation which is resonance stabilized. Now we'll discuss two more examples. And the first one is this. This is the first one. Now, which one is more reactive towards SN2? Now, in this case, this one is more reactive. Although both are primary, but this one is more reactive because the alpha carbon is more exposed, has less crowding. The methyl group branching is there, but branching is at the gamma carbon. In this case, the branching is there, but at the beta carbon. So the first one is more reactive. Now one more example. Out of these two, which one is more reactive towards SN2? Now see, both the compounds of the same alkyl group, but this one is now more reactive because Ci bond is weaker than CCl, is weaker than CCl, and I minus is a better leaving group than Cl minus. Better leaving group than Cl minus. So this way you can decide the reactivity of the haloalkane towards SN1 or SN2. Now next we'll discuss about the stereoisomerism, mainly optical isomerism. Stereoisomerism. And the first point, isomerism due to a different arrangement of atoms or groups in space. Second point, we have two types of stereoisomerisms. We have two types of stereoisomerism. The first one is geometrical isomerism is due to the presence of a double bond and the like groups either on the same side of the plane, either on the same side of the plane, then it is called cis isomer, or on the opposite side of plane. Then it is called a trans isomer. For example, this is called a cis isomer and this one is called a trans isomer. This is geometrical isomerism. Now, second type is a optical isomerism, which is in your syllabus in class 12th, optical isomerism. I'm using this as an abbreviation for optical isomerism. Now, optical isomerism is due to the presence of non-superimposable mirror images. Non-superimposable mirror images. For example, this is letter B. Now, if you take its mirror image, this is its mirror image, and these two are non-superimposable, so we'll show optical isomerism. Another example is this letter P. Again, the mirror image is not superimposable, but this mirror image is exactly superimposable, so no optical isomerism. So no optical isomerism. Like you cannot wear a left hand glove in the right hand. That is the meaning of optical isomerism. Now, in organic compounds, optical isomerism is possible when the carbon atom is sp3 hybridized with a tetrahedral arrangement, with a tetrahedral geometry. Now, this is sp3 carbon. It has 4 valences free. And all 4 valences of sp3 carbon should be satisfied by 4 different groups. Satisfied by 4 different groups. For example, A, B, E, and F. Now, carbon atom attached to for different atoms or groups is called a chiral carbon or asymmetric carbon. Chiral carbon or asymmetric carbon, and we show the asymmetric carbon or chiral carbon by using star as a left superscript. Now, first of all, now I'll take some example to show how to identify the chiral carbon, if any present. For example, this is called a lactic acid. So this lactic acid contains this carbon, a chiral. Now, second example is this has a common name called a glyceraldehyde. Also contains a chiral carbon, this. Now, one more example. Suppose I'm giving the name, then you draw the structure, then identify the chiral carbon present or not present. For example, this, you are given a 3-chloro hex 1-ene. So we draw the structure. The structure of 3-chloro hex 1-ene is this, and it contains a chiral carbon. So this is my chiral carbon, and it contains 4 different groups. One is chlorine, one is this vinylic group, third different group is hydrogen, and the fourth one is this propyl group. So first of all, you should know how to identify the chiral carbon. Then we represent the molecule. We represent the molecule by using a Fisher projection formula. Fisher projection formula, me using vertical and horizontal line. For example, we have a lactic acid in which the carbon number 2 is chiral. Total there are 3 carbons. So we take the maximum number of carbons on the vertical line. And the point of intersection represent the chiral carbon. In this case, it's a number 2. And in the Fisher projection, the most oxidizable carbon should be at the top. Most oxidizable carbon should be at the top. So we have a carboxylic acid at the top of this vertical line and the methyl at the number 3 position at the bottom. Now at number 2 carbon, we have a choice. I can write either OH on the right, H on the left, or I can write OH on the left and H on the right. But there is no change in the carboxylic acid group and the methyl group. But if you look at these two structures, these two are non-superimposable mirror images. So these are called optical isomers. Non-superimposable mirror images called optical isomers, also called enantiomers. Enantiomers. They're also called enantiomers. So non-superimposable mirror images are called enantiomers. But if you look at the structure of the enantiomers have same functional group, so their chemical properties are same. Chemical properties are same. They also have the same arrangement of carbon atoms, so same physical properties. Same physical properties. Then what's the difference? The only difference in the two enantiomers is in the reactivity towards a plane polarized light. Plane polarized light. And you can use this abbreviation PPL. Now, what's a PPL? What is plane polarized light? Now, ordinary light, which we see in everyday life, has components, vibrations, oscillations in all three planes. So we represent the ordinary light like this. This is ordinary light. And plane polarized light has vibrations, oscillations, components only in one plane. Oscillations only in one plane. And we convert the ordinary light into a plane polarized light by using a filter which is called polarizer. So this is my ordinary light. This is ordinary light. We allow this light to pass through a prism. This is called nickel prism, which is a calcite crystal. Which act as a polarizer. And the light which comes out of this polarizer is called the plane polarized light, which has vibrations only in one plane. Then we allow this plane polarized light to pass through a sample. So this is my sample. And I observe the behavior of the plane polarized light in the eyepiece. Now two options are there. Either the light will pass through the sample without any deflection, means we are getting the light as it is. So no deflection. So we use the term that sample is optically inactive. Optically inactive. Second option is light may interact with the sample and gets deflected. Then two options are there. Either the light can deflect in a clockwise, like this, or the light can deflect in an anti-clockwise. So this is called anti-clockwise. But in both the cases, the sample is called optically active. This anti-clockwise is called a levorotatory. We use a minus sign. And this is called a clockwise rotation. This is called dextrorotatory. Or we use a sign plus. And this deflection of a plane polarized light by sample is called optical rotation. Deflection of a PPL by sample is called optical rotation. And the angle through which it rotates and the angle through sample rotates the plane polarized light is called angle of rotation. Maybe plus 20 degree, maybe minus 15 degree, called angle of rotation. Right. Now we take one example. For example, this is given a sample of now if you look at the two enantiomers of lactic acid like these two, which are non-superimposable mirror images, but out of these two, which one is dextro, which one is levo, I don't know, because that's an experimental quantity. But yes, if you know this is a dextro isomer, this will be 100% levo isomer. But first you have to identify one of the isomer you have to identify is a dextro or levo. So presence of one chiral carbon gives you one pair of enantiomers. Presence of one chiral carbon gives one pair of enantiomers. Two isomers, but one pair of enantiomers. Now one more question now. Question is a sample of two chlorobutane is optically inactive. Explain. Optically inactive. Explain. Now, first of all, we draw the structure of 2-chlorobutane. Now, if you look at the structure of 2-chlorobutane, it contains a chiral carbon. The number 2 carbon is a chiral carbon, so it should be optically active. It should be optically active. But since sample is inactive, means sample is not a pure isomer. Sample is not a pure isomer. Sample is a mixture of two enantiomers in equimolar amounts. Equimolar amounts. As a result, effect of one enantiomer on PPL is exactly cancelled out by the second isomer, second enantiomer. exactly cancelled because they are in the ratio of 1:1. So what is this mixture known as? So the mixture containing two enantiomers in 1:1 mole ratio is called racemic mixture. Racemic mixture. And racemic mixture is optically inactive. It is optically inactive. And we represent like this. This is my dextroisomer 1 mole. This is my levoisomer 1 mole. And both these are enantiomers. Optically active enantiomers. So we're mixing them exactly in the ratio of 1:1. They form a racemic mixture represented by this. This is called racemic mixture, plus minus, and is optically inactive. This process is called racemization or this is called racemic modification. But we can also convert the enantiomer, we also convert the racemic mixture back into pure enantiomers, means we are splitting the racemic mixture into two enantiomers. This is called a resolution. But remember, resolution can take place only of a racemic mixture. So if we write my compound is capable of being resolved or the resolution is taking place, it means my compound is a racemic mixture and is optically inactive but contains a carbon. So if any compound is resolvable, means the compound is a racemic mixture, is not a pure isomer. It means the compound is optically inactive, is optically inactive. It means the compound contains a chiral carbon. So it helps in writing the structure. Compound contains a chiral carbon. Now, for example, you are given this carboxylic acid A. With a molecular formula C5H10O2 is a resolvable acid. Question is, what is the structure of acid A? What is the structure of acid? Now, since this acid is resolvable, it means this acid is a racemic mixture. It's not a pure isomer, inactive, but it contains a chiral carbon. So the structure is this. Only one structure is possible. This is our carboxylic acid, which contains a chiral carbon. This is A. Now we will discuss about the stereochemistry of SN1 and SN2 reaction. Stereochemistry of SN1 reaction. First we'll discuss about the SN1 reaction. And SN1 reaction is a two-step mechanism. The reaction proceeds via carbocation. Now, suppose you are given the starting compound and this carbon is called a chiral carbon. Assume it's a pure isomer. Assume it's a plus. Think positive. Take positive. Now, first step is the loss of chlorine. This is bond breaking. Is the rate determining step, and it gives you a carbocation. So this is my carbocation form. It's a planar, flat. As a result, the nucleophile now can attack from any side of the plane, above the plane, below the plane. So when the nucleophile attacks, it gives you two isomers. One, when the isomer obtained when the nucleophile attacks from above the plane. This. Second, when the nucleophile attacks at the carbon from below the plane. And since both the isomers are obtained in equal quantity, the product is a racemic mixture. Product is a racemic mixture. It means my product is optically inactive. So in SN1 reaction, optically active substrate means the reactant, optically active substrate gives, first point, optically inactive product. Gives a product which is resolvable, which is a racemic mixture and is resolvable. Is a racemic mixture and is resolvable. And the converse is also true. Converse means if optically active substrate, gives a resolvable product, means, first point, the product is a racemic mixture. Second, product contains a chiral carbon. Means the reaction proceeds via carbocation. And follows SN1 mechanism and is given by highly crowded haloalkanes. Given by highly crowded haloalkanes. Means the reactivity order is 1 degree, 2 degree and 3 degree haloalkane. So all these points are interconnected. The next is a stereochemistry of SN2. Of SN2 reaction. Now in SN2, if you remember, the nucleophile attacks to the carbon from the backside. It's a one-step mechanism, proceeds via transition state. For example, this is given starting compound is a substrate, where D stands for deuterium. Again, we assume it's a pure isomer. Again, we assume it has a plus. Now, this is my nucleophile, attacks to the carbon from the backside, results in the loss of chlorine. So, this is the rate determining step, arrival of nucleophile and the departure of chlorine both takes place simultaneously. And this is called my transition state. Bond formation and bond breaking both takes place simultaneously. This is slow step, and then it decomposes to give my final product, which is this one. Only one isomer is obtained. It's a pure isomer. You won't get mixture in this case. It's a minus isomer. Now why minus? Because in SN2, a nucleophile attacks at the carbon from the direction opposite to the leaving group. So there is a change in the sign of optical rotation. There is a change in the sign of optical rotation. And this is called inversion of configuration, or this is called Walden's inversion. Walden's inversion. So if there is a change in the configuration, it means the mechanism is SN2, proceeds via transition state given by less crowded haloalkanes. So if optically active substrate gives optically active product with opposite configuration, means first point, the mechanism is SN2, means proceeds via transition state, means given by less crowded haloalkanes. Otherwise, nucleophile will not be able to attack from the backside, given by less crowded haloalkanes. So this is the reactivity order then. So all these points are interconnected. Now we'll take one or two examples. For example, this question is, how many enantiomeric pairs obtained on monochlorination of isopentane. The question is how many enantiomeric pairs obtained. So how to attempt this question? Now look at the steps. The first step is you write the structure of the isopentane. This is the structure of isopentane, and isopentane contains 4 different sets of hydrogen. These two are identical. This is number 2, this is number 3, number 4. So there are 4 sets of hydrogens. So you will get 4 products, and these are the 4 products obtained when you react this compound with chlorine in the presence of light. So these are the 4 isomers formed. The first is this one. We are replacing the hydrogen from the set number 1. Then we replace hydrogen from the set number 2. Gives this product. Then we are replacing the hydrogen from the set number 3. And finally, we replace the hydrogen from the set number 4. Give this product. Now you see, out of these 4, which one contains a chiral carbon? Now chiral carbon is present in the first, so it gives you 1 pair of enantiomer. Then compound 3 contains a chiral carbon, gives you 1 pair of enantiomers. So isopentane on reaction with chlorine and light gives 2 pairs of enantiomers. 2 pairs of enantiomers. So this is the way you have to apply the stereochemistry. One more question. The question is this, that plus C7 C7H15Br on hydrolysis gives plus minus C7H15OH. Now question is write the mechanism with stereochemistry. With stereochemistry. Now first point is that a pure enantiomer, pure substrate is giving us the racemic mixture. Pure substrate is giving you a racemic mixture which is optically inactive. Plus gives plus minus. It means the mechanism is SN1 proceeds via carbocation given by highly crowded haloalkane. So my substrate is this CH3, this is C2H5, and this is C3H7, and this is my chiral carbon. This is plus isomer. So the first step is the loss of Br minus. The loss of bromide gives a carbocation. So this is my carbocation. And which is planar, flat. Then it reacts with hydroxide ion to give me a mixture. So this is my mixture. plus this. So this is the racemic mixture because chiral carbon is present, but this is optically inactive. Both the isomers are obtained in equal quantity. So this is called a racemic mixture. So this is all about the haloalkane and haloarenes. Now we start with the reactions of haloalkanes. And there are three categories of reactions of haloalkanes. Reactions of haloalkanes. There are three categories of reaction. The first one called nucleophilic substitution. Nucleophilic substitution. And since X negative is the best leaving group, X can be replaced by any group of your choice. Now, second category of reaction is, this is called elimination, also called dehydrohalogenation, means the loss of H and X from the haloalkane. D as a prefix means removal, loss. And the third category of reaction is with metals. With metals. So we start with nucleophilic substitution. Nucleophilic substitution reactions. So in general, we represent the nucleophilic substitution as this. This is Rx. This is my incoming nucleophile. And the product is RNU. This is double displacement reaction, non-redox, and X can be displaced by any group of your choice. So I can write number of reaction, whichever group you want to add, you want to replace X by, take a sodium compound of that group. For example, this is Rx, and my aim is to replace X by OH. So what I will do, I will take the sodium compound or the potassium compound of OH like this, either NaOH or I will write KOH, but in aqueous medium. Because NaOH and KOH dissolves in water to give OH negative. So you can write aqueous KOH, you can write dilute NaOH, anything you can write. And the role of aqueous alkali is to replace the X by OH. You can replace 1, you can replace 2, you can replace any number of X atoms. This is called hydrolysis. Similarly, if you want to replace X by OR dash, so my aim is now to replace X by OR dash. So what I will do, I will take the sodium compound or potassium compound of this. Now this is called sodium alkoxide. And these two alkyl groups, they may be same, they may be different. Now this function group is called ether, and this method of preparation of ether is known as the Williamson's synthesis. It's very, very important. Williamson's synthesis. But in this Williamson synthesis is an example of a SN2 mechanism. Therefore, R has to be less crowded than R dash. So in Williamson synthesis, R has to be less crowded than R dash. Now this is CH3, CH double bond CH2. We are reacting it with HBr in dark. Now when we are reacting the propane with the HBr in dark, it follows Markovnikov addition and gives 2-bromopropane. And this 2-bromopropane, when treated with aqueous alkali, KOH, NaOH, it gives you propane 2O. Now similarly, we have one more example. Suppose my aim is to prepare this ether. It's a methyl isopropyl ether. Now look at the two alkyl groups which are directly bonded to oxygen. Now this one is less crowded, so you take methyl as a halogen compound. So CH3X, and the other one as a nucleophile Na plus O negative CH3 and the CH3. So this is the Williamson synthesis. Now some more examples, some more reactions, nucleophilic substitution reactions of haloalkanes. Like this is Rx, and our aim is to replace X. So if you want to replace X by this C triple bond H, CH or R dash. So it means my aim is to replace X by this to prepare the higher member of the alkyne series. So I use a sodium compound of this. It can be H, it can be R dash. My aim is to prepare this functional group. Again, R and R dash may be same. So what I'll do, I'll take the sodium compound of this. This function group is called ester. So I use Na plus O, C double bond O and R dash. Only then the ester can be prepared. Now we have two important, but remember all these reagents you can use only when the parent compound is halogen. You can't use this sodium compound of ester with alcohol, no, or with alkenes, no. So only with the halogen compound you can use these reagents. So I have now two examples. One is how do you convert ethanol into but1 Now, first of all, you write the structure of these two compounds. This is my ethanol, and this is but1. So, if you compare the structure of these two, this ethyl group is already present. So, my aim is to replace the OH by this. But I can't replace OH directly by C triple bond CH. I have to convert first alcohol into halide. And the easy method is use PCl5 or SOCl2, convert this into chloride. Then you select your nucleophile or incoming reagent. So now I will replace this by using sodium compound of C triple bond CH. So this is the way you have to perform the conversions. Now some more nucleophilic substitution, like this is haloalkane, and my aim is to convert this into RSH. This is called alkyl. R stands for alkyl, and this group is called a mercaptan. Mercaptan. So I can use again the sodium compound of SH. This is called sodium hydrogen sulfide. Similarly, suppose my aim is to prepare this one. This is called amine. This is called in fact primary amine. Any compound containing NH2 group is called primary amine. So what I do, I react this compound with ammonia. Ammonia can act as a nucleophile because it has a lone pair of electron present. So basically I can change my X into any function group of my choice. Now I'll give you one example. Now this is an example given to you. Now we are reacting this with NaSH. Now my question is, what is the product form? Now in this case again two chlorines are present, but the chlorine which is directly bonded to benzene cannot be replaced, because that group is in resonance with the benzene. So chlorine on the side chain only will be replaced by SH. So my answer is this. So only this chlorine will be replaced. Now we'll discuss two very, very important reactions of the haloalkanes in the nucleophilic substitution category. And the first one is reacting the haloalkane. Suppose my aim is to convert haloalkane into cyanide. This group is called cyanide. This group is also called nitride. So what I do, I react this compound with a sodium cyanide or potassium cyanide, but in alcoholic medium. So alcoholic NaCN, alcoholic ACN. Now, in this case, the cyanide is obtained. This has a common name called alkyl. This R stands for alkyl. CN stands for cyanide. So this is called the common name. Now, in IUPAC system, we start numbering with the cyanide carbon on the alkyl group side, and this nitrogen comes as a suffix called nitrile. So IUPAC name is alkane. Full name you have to write. You don't have to drop any E. Retain the last E of the hydrocarbon, and then you write nitrile as a suffix. This is the IUPAC name. For example, if you are given this, now this has a common name, ethyl cyanide, but its IUPAC name is propane and nitrile. So in the IUPAC system, the cyanide carbon has to be included. Now, when we react this haloalkane with AgCN alcoholic solution again, it gives us RNC. This group is called isocyanide, carbylamine. So it has a name called alkyl carbylamine or alkyl isocyanide. Now the question comes, why the difference in the product form? That one is giving you isocyanide, other one is giving you cyanide. The reason is very simple. In NaCN, potassium cyanide or in sodium cyanide, sodium carbon bond is ionic. Potassium carbon bond is also ionic. So carbon is negatively charged, is the nucleophilic center. Attacks on the R group of Rx, R group of Rx to form RCN, like this. It gives RCN. Now, in case of silver cyanide, silver carbon bond is covalent. Right? So carbon has no negative charge. Now, due to the presence of lone pair of electron, nitrogen is the nucleophilic center. So nitrogen has a lone pair, is the nucleophilic center. Attacks at the R group of Rx to form isocyanide. Isocyanide, like this. So this is Rx, this is AgCN. So in this case, the attack is through nitrogen, not through carbon. So it gives you RNC plus AgX. So RCN, so CN minus and NC minus, these two groups have the same formula, but different linking atoms. One can link through carbon, other through nitrogen atom, but different linking atoms are called ambident nucleophiles. I can use my left hand, I can use my right hand also. Ambident nucleophiles. Ambident groups also you can write. Ambident nucleophiles or ambident groups. But Using cyanide is a very good method to increase the number of carbon atoms. So, alcoholic KCN or alcoholic NaCN can be used to increase carbon atoms. I can step up. I can change my chloromethane into chloropropane. I can change my ethanol into propanol. Number of carbon atoms. So this is a method to step up the series. Step up series. So this is the flow chart, how you step up the series. Now, but remember, KCN or NaCN can be used only with halogen, not with any other compound. So this is the starting RCH2Cl can be used with ethanolic KCN to give me this product. Now once the CN is formed, CN can be changed into number of other functional groups. So I can reduce this by using LiALH4. It gives me RCH2 CH2 NH2. This is called primary amine. Any compound having NH2 group is called primary amine. But I can also hydrolyze CN by using dilute sulfuric acid into carboxylic acid. So CN group can be changed into carboxylic acid, which can be reduced with LiALH4 to give alcohol. This is loss of oxygen and gain of hydrogen. This is a primary alcohol, but amine can also be hydrolyzed to alcohol using nitrous acid, right? And once OH is formed, I can change this into chlorine by using PCl5. So if you see this now, I can change one chloroalkane into another with one more carbon atom. So chloroalkane to chloroalkane with one carbon more. Now suppose you want to step up in the alcohol series. Again, you can't use KCN with alcohol. You first change the alcohol into CN like this, using PCl5, SOCl2. And then follow the sequence and stop your reaction at this stage. So alcohol to alcohol, you can step up. Now suppose you want to step up in carboxylic acid, you want to change ethanoic acid into propanoic acid. Again, you can't use KCN with ethanoic acid, carboxylic acid. So you have to change first the carboxylic acid into alcohol using lithium aluminium hydride, and then follow the sequence of steps and change the carboxylic acid into a carboxylic acid with one more carbon. Similarly, you can step up in the amine series. Now this is my amine. So I'll convert my primary amine first into alcohol using HNO2, then follow the sequence of steps and change amine into amine. So amine to amine with one carbon more. But you can cross the series also. Like you can change acid with 2 carbon into alcohol with 3 carbon. Now I'll discuss, this is called the flow chart to step up. To increase the number of carbon atoms. Now I'll discuss 2 examples with you. The first one is, how do you convert ethanol into propanoic acid? So 2 carbon into 3 carbon. So this is my sequence of steps. Starting compound is ethanol. First step is using SOCl2 PCl5, changing this into chloride. Then using KCN, changing this into cyanide. And then hydrolysis. Hydrolysis, you can simply write H plus ion. It changes to a propanoic acid. This is propanoic acid. Now one more question. Convert ethene into propane nitrile. First of all, you should know propane nitrile has how many carbons? Now, propane nitrile is CH3, CH2, and Cn. Including carbon of the Cn, there are 3 carbons. And this is my starting compound ethene. Now, you can change. First, you prepare the halogen compound. So, we are reacting it with HCl, HBr, anything you can write, but in dark. It gives you CH3, CH2, Cl, and then using alcoholic KCl. Right? So this is the usefulness of using cyanide in organic chemistry. It's a very important synthetic reagent. Via this, you can prepare number of compounds. Now, one more nucleophilic substitution, that reacting the haloalkane with KNO2, this is called potassium nitrite. You can also use sodium nitrite, NaNO2. It gives you RON. This has a name called alkyl nitrite. But in this case, if you look at the structure of the KNO2, it's ionic. Potassium-oxygen bond is ionic. So the oxygen is the nucleophilic center, attacks at the alkyl group to give oxygen is the nucleophilic center, attracts the R group of Rx to form RON. But if you react this compound with AgNO2, silver nitride, it gives a nitroalkane. So this is called nitroalkane. So in AgNO2, silver oxygen bond is again covalent, and due to lone pair on nitrogen, and nitrogen also has a size comparable to carbon, so nitrogen is a nucleophilic center. In this case, nitrogen is the nucleophilic center. So it gives nitroalkane. So ONO minus and NO2 minus is also an example of ambident nucleophile. Ambident nucleophile. Now we'll discuss one very important conversion. So we have 3 conversions of this type. 2 we have already discussed: propane into 1-fluoropropane, propane into 1-iodopropane, now propane into 1-nitropropane. This is very important conversion. Convert propane into 1-nitropropane. So first of all, you write the structure. This is my starting compound propane, and my aim is to prepare 1-nitropropane. So my aim is to add NO2 group at this carbon, but I can't add NO2. The only group which you can add to this carbon is the bromine using HBr in the presence of peroxide, anti-Markovnikov addition. You have no other choice in the first step. So what we do, we write HBr in the presence of peroxide. Any peroxide you can write, benzoyl peroxide, just peroxide. Now the addition takes place according to anti-Markovnikov rule. And then we replace, once we have a halogen, then our work becomes very simple, because X is a very good living group, halogen is a very good living group, and halogen can be replaced by any group of your choice. You just decide, I want this group. So now our aim is to replace bromine by NO2, so we write AgNO2. But I've seen many students, they write HNO3 and H2O4 to add NO2 group. No, that's incorrect, because HNO3, H2O4, they combines to give NO2 plus, not NO2 minus. And NO2 plus is an electrophile. So this NO2 plus can replace only H of the benzene, not the H of any hydrocarbon. We want NO2 minus, That's why we are using AgNO2. So this is the first category of reaction. Now the second category of reaction is the dehydrohalogenation. Dehydrohalogenation. Now dehydrohalogenation means elimination. It's the loss of H positive and X negative. So we are removing H positive and X negative from the same haloalkane. But since haloalkanes are not very strong as they give H plus ion with difficulty, that's why this dehydrohalogenation takes place in the presence of a strong basic conditions. Requires a strong basic conditions. So these strong basic conditions are hot and alcoholic KOH or NaOH. And they combines to give this alkoxide ion, which is a very strong base. It's stronger than OH negative. So you should remember that aqueous KOH results in the formation of alcohol, nucleophilic substitution, but alcoholic KOH results in the removal to form alkene. So what we do in this case, when we remove HX, we remove this X minus from alpha carbon and we remove H plus from beta carbon. As a result, the double bond is formed between alpha and beta carbon. Double bond is formed between alpha and beta carbon, like this. So this is my halogen. This is a strong base we are using. It removes H plus. This electron pair will shift toward this side, forms a double bond between alpha and beta carbon, loss of this. So the entropy is also increasing in this reaction, and that is a driving force. That helps in shifting the equilibrium in the forward direction. So it gives me alkane. This is called alpha beta elimination or simply beta elimination. Nowadays we just use beta elimination. Now we take some example. Now this is the first example, CH3, CH2 and the Br. Now in this case, this is my alpha carbon and only one beta carbon is present. So when we use hot and alcoholic KOH, it gives one and only one alkene, that is called ethene. Now second example, this is one bromopropane. It's a hot and alcoholic KOH again. Now this is alpha carbon and only one beta carbon is present. Again, only one alkene called propene. Next example, CH3, CHBr. Slowly will increase the level also. This is alpha carbon. There are two beta carbons, but both the beta carbons are identical. So I can remove H plus ion from any beta carbon. Now again we are writing hot and alcoholic KOH, and again one and only one alkene is formed, and this is called propane. Now next example is this, CH3, CH2, CHBr and CH3. Now in this case there are two different beta carbons present, so we differentiate them by writing beta and beta dash. This is 2-bromobutane. Now when you write this compound with hot and alcoholic KOH, you can write this way also, KOH, alcohol and heat. Now I have two choices now. I can remove H plus ion from the beta carbon, or I can remove H plus ion from the beta dash carbon. So two alkenes are formed, and these two alkenes have position isomers, but1-ene and but2-ene. Now when you have more than one alkene possible, then you have to follow the Syllabus rule. Now, Syllabus rule states that simple statement that the major alkene is one which contains a minimum number of hydrogens at the double bonded carbon atoms. So butene, if you see butene, you have only two hydrogens present at the double bonded carbon. This has one H, this has one H. So total you have only two hydrogens present. So this is a major alkene, whereas one butene has three hydrogens at the double bonded carbon. This contains one H, this has two hydrogens. So total you have three hydrogens, right? So this is a minor alkene. So if you are given this type of example, you have more than one different beta carbon, you write all possible alkenes, then you apply the Syllabus rule, select the major product and write your answer. Now suppose you are given this. And we are reacting this compound with hot and alcoholic KOH. Now in this case, this is my alpha carbon. There are two different beta carbons present. So first I'll write all my possible alkenes in my rough work. So these are my possible alkenes. This is the first one, plus this is my second one. But this contains no hydrogen at this carbon. This carbon has only one H. This carbon has one H. This carbon also has one H. So this contains minimum number of hydrogens. So this is my major alkene. So this is the way you have to select the final major product. The next is what the usefulness of this reaction. This dehydrohalogenation is used to change the position of the functional group. To change the position of functional group. Suppose you want to convert 1 chloropropane into 2 chloropropane or propane 2-ol into propane 1-ol, you have to proceed via alkene. So first step will always be the formation of alkene. The given compound, first you change this into alkene, and after that you follow add HX according to Markovnikov curve or anti-Markovnikov rule depending upon the conversion given. Anti-Markovnikov. So we'll discuss two examples now. The first one is this. But aim is to convert the given compound first into alkene. So question is convert 1 bromopropane into 2 bromopropane. So this is our conversion. So you have to change the position of bromine from number 1 to number 2 carbon. So first step is to convert the 1 bromopropane into alkene using hot and alcoholic KOH. And as far as your syllabus is concerned, there are two best methods to prepare alkene, either from haloalkanes using dehydrohalogenation or from alcohol using dehydration. So this is propene, and then we add HBr according to Markovnikov rule, and it gives you 2-bromopropane. Convert 2-bromopropane 2-methyl propane into 1-bromo 2-methyl propane. So again you have to change the position of the bromine from number 2 to number 1. So this is my starting compound. If you see these two structures, the carbon skeleton is same. Only the position of the bromine is so this is called tertiary butyl bromide, the common name, and this is called isobutyl bromide. So the first step is, since you already given the haloalkane, so we convert this into alkene first. So this is the first step, using a hot and alcoholic KOH, and there is 1 alpha and 3 beta carbons are present, and all 3 beta carbons are identical. So you can remove H from any beta carbon, so only one alkene is possible. And then you add HBr according to anti-Markovnikov rule in the presence of organic peroxide. So this is the way by which we can change the position of the functional group. So this is all about the dehydrohalogenation of haloalkanes. Now after nucleophilic substitution reactions and the dehydrohalogenation, now we will discuss the reaction of haloalkanes with metals. So the heading is a reaction with metals. And the first reaction is with the sodium metal. This is class 11th repeating with sodium metal. Now haloalkanes on reaction with sodium metal in the presence of dry ether. Now dry ether is used as a solvent, and dry ether means it's a anhydrous ether without water. It forms RR. This is called alkane, and the side product is NaX. This is called alkane. Now if you look at this final product alkane, the new bond has been formed between the alpha carbon atoms. So this is a new bond between the alpha carbon atoms. So always form a new bond between the alpha carbon atoms. Now this reaction is called a Wurtz reaction. This is called Wurtz reaction. Now this is one example, and whenever you want to write example, you write the simplest one. For example, CH3Br on reaction with sodium in the presence of dry ether gives CH3 and CH3. The new bond has been formed between the alpha carbon atoms. Now we'll take one more example in the form of a question. Now this is CH3, CH double bond CH2. This is alkene. So we are adding HBr in dark according to Markovnikov's rule gives CH3CHBr and CH3. Now we are reacting it with sodium in the presence of dry ether. Now you have to form a new bond between the alpha carbon. So CH3, CH, this is your alpha carbon, and form a new bond between the alpha carbon atoms. So the answer to this question is 2,3 dimethyl butane. Dimethyl butane. So this is a reaction with sodium metal. Now second reaction is with magnesium. Now haloalkanes on reaction with magnesium, again in the presence of a dry ether, anhydrous condition gives an organometallic compound called Grignard reagent. This is a very versatile reagent in organic chemistry called Grignard's reagent. This is also called alkyl magnesium halide. Now there is a bond between the metal and carbon. That's why the name is given organometallic compound. And these magnesium compounds are highly reactive, and are decomposed by any compound containing active hydrogen. For example, the Grignard's reagent can be decomposed by water, can be decomposed by alcohol, phenol, carboxylic acid. So all these compounds can decompose the Grignard reagent to a hydrocarbon. For example, this is our Grignard's reagent. We are reacting with a compound containing active hydrogen. So it gives RH. So MgX has been replaced by H, and our side product is MgX and Z, where Z can be OH, can be RO, can be phenyl O, can be RCOO minus. So it can be any compound out of these groups. So one example is, this is CH3 MgBr. When treated with water, it decomposed to give CH3H. This is called methane. And the side product is MgBr and OH. And because of this reason, Grignard's reagent always prepared under anhydrous conditions. So no water should be present, no moisture, anhydrous conditions. Now we take one example. Now this is my starting compound RBr. And this on reaction with sodium gives me this compound CH3, 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 and CH3 and CH3. This is the compound obtained when we react the RBr with the sodium, and this on reaction with magnesium gives A, which on reaction with D2O, D2O is a heavy water. It's containing isotope of hydrogen, and you know isotopes have the same properties. Like water replaces MgX by H, D2O will replace MgX by D. So my question is, find the structure of R, A and B. Now since RBr is giving this compound hydrocarbon on reaction with sodium, which is symmetrical compound, you divide this exactly into two parts, it gives the R value. It gives the structure of R. So my R is this, it's a tertiary butyl group. This is our R. Now the structure of A we can write, because once we know the structure of R, I can write the structure of A. So my structure of A is tertiary butyl magnesium bromide. Then to write the structure of B, you replace the MgBr by D. So this is structure of B. So this way you can attempt the questions. Now next, now we'll discuss about the haloarenes. Haloarenes, mainly halobenzene. Haloarenes means you have a halogen directly bonded to the benzene ring. Directly bonded to benzene ring. These are also called aryl halides. So we use the term aryl halide only when the halogen is directly bonded to benzene. For example, this is called halobenzene. halobenzene. For example, this is chlorobenzene. And when you have one group on the benzene, you can place it anywhere. This is a second example called bromobenzene. Bromobenzene. When the second group comes on the benzene, then we have three structures possible. One is this position, which is called ortho. 1 and 2 position is called ortho. So its common name is ortho dichlorobenzene. And this has a IUPAC name 1,2 dichlorobenzene. 1,2 dichlorobenzene. Now, second example is you have two different halogens present, but now they are present at the meta position. Meta position is 1 and 3. So this is called meta. Then you arrange the two halogens alphabetically. So its name is common name is meta-bromo-chlorobenzene. Now it's the IUPAC name. You start numbering with the bromine carbon because the bromine B comes first in the alphabetical order. So its IUPAC name is 1-bromo 3-chlorobenzene. Then we have one more example. Now this is benzene with two groups at 1 and 4 position. So this is called para. So its common name is para-chlorotoluene. So we are taking toluene as a parent hydrocarbon. In the IUPAC system, the chlorine gets a preference over methyl. So we start numbering with the chlorine carbon and methyl carbon is number 4. So its the IUPAC name is 1-chloro 4-methyl benzene. Now one more example in which the benzene is present, but my functional group is on the side chain, not directly bonded to benzene. When the functional group is present at the carbon next to the benzene, then it is called benzyl. Now this compound has a common name called benzyl chloride. Benzyl chloride is a common name. Now since benzene is present but the function group is on the side chain, so the benzene comes as a prefix. And the prefix for benzene is called phenyl. So the IUPAC name is chlorophenyl methane. So you should know when to write methyl, when to write benzene and when to write phenyl. Now we write benzene when the functional group is directly bonded to benzene, and we write phenyl when the functional group is on the side chain. One last example. Now this is an example given in which the benzene is present, double bond is present, as well as the halogen is present. Now out of these three, the double bond gets a preference, so we start numbering with this carbon. And there are two prefixes, one is chloro, one is called phenyl. So arrange them alphabetically. So its name is 3-chloro, 1-phenyl, and then we write prop 1E. So this is about the nomenclature of haloarenes. Now we discuss about the preparation of halobenzene, mainly halobenzene. So the heading is preparation of halobenzene. And we have number of methods to prepare halobenzene. And the first method is called a direct halogenation of benzene. Direct halogenation of benzene means benzene H has to be replaced by halogen. But remember, Hydrogen of the benzene can be replaced only by electrophile. So H of benzene can only be replaced by an electrophile E positive. So the reactions are called electrophilic substitution reactions. Now, for example, and one more point, all these electrophilic substitutions requires the presence of a Lewis acid as a catalyst. And Lewis acid helps in the formation of electrophile. Lewis acid helps in the formation of electrophile E positive. Now, for example, we are reacting the benzene with X2, where X can be chlorine and bromine in the presence of FeX3 as a Lewis acid and catalyst. It gives us halobenzene plus the side product is HX. Now this FeX3 helps in the formation of electrophile X positive like this. So this is XX and this is FeX3, which is a Lewis acid electron pair acceptor. So it accepts electron pair from this X, right, to give X with a positive charge, and this X has only 6 electrons, so this is my electrophile, and FeX4 negative. So this is my electrophile, and once this electrophile is formed, then it attacks on the benzene ring to give the halobenzene. Now example, like we are reacting the benzene with chlorine in the presence of FeCl3, it gives chlorobenzene and the side product is HCl. Similarly, benzene on reaction with bromine in the presence of FeBr3 gives bromobenzene plus HBr. Now iodination of benzene takes place, and since iodination of benzene is reversible, iodination of benzene is reversible, therefore the reaction takes place in the presence of an oxidizing agent. In the presence of an oxidizing agent which oxidizes Hi to iodine and prevent backward reaction. Now this is the equation involved. This is benzene on reaction with iodine in the presence of an oxidizing agent, either HNO3 nitric acid, or we can use HiO3 iodic acid. It gives iodobenzene plus Hi. And HiO3, being an oxidizing agent, oxidizes the Hi to iodine and prevents the backward reaction. And direct fluorination does not take place. Now next example is, suppose you are given toluene is a homologue of benzene. Now in this case, if you want to replace H of the benzene ring, then we use chlorination in the presence of FeCl3, and since methyl is electron donating group, it is orthopara directing. Methyl group is orthopara directing, so the chlorine comes either at ortho position or at para position. So the two isomers are formed in which the para is generally the major product This is orthochlorotoluene and this is parachlorotoluene. But if you want to replace H of the methyl group by chlorine, now methyl is saturated carbon. It's a saturated group. And the hydrogen of the saturated carbon can be replaced by halogen only in the presence of a light or at high temperature. For example, when toluene is being treated with chlorine in the presence of light, then the hydrogen of CH3 will be replaced, not the benzene ring. So it gives a benzyl chloride, not chlorobenzene derivative. One more example, whenever we use chlorine in the presence of light, you have to replace the H of the saturated carbon and the saturated carbon which is next to the double bond. For example, one more example, suppose we are reacting this now with bromine in the presence of a light and heat both. Now this is my saturated carbon which is next to the double bond. They both are identical, so you can replace any H of the saturated carbon by bromine. So the answer is this one. One more example. Now suppose we are given this. This is para-nitroethylbenzene. And we are reacting it with again bromine in the presence of light and heat. Now it will replace the hydrogen of the saturated carbon next to the double bond, means this carbon. Benzene remains unaffected, so my answer is this. So you read the conditions very carefully. Benzene H can be replaced by halogen in the presence of Lewis acid, but saturated carbon hydrogen can be replaced only by halogen in the presence of light or high temperature. So the answer is this. Now, second method to prepare aryl halide is from benzene, diazonium chloride. In short form, we can write BDC. Now, first of all, what's the meaning of diazonium? Di means there are two, and azo stands for nitrogen. So there are two nitrogen on the benzene ring carrying a positive charge. You know, all cations have an ending in IUM. So its structure is this. This is benzene, and the two nitrogens are present with a positive sign, and then chloride. Chloride symbol is Cl negative. This is called BDC. Now, remember in this case, a salt, just like NaCl, and N2 plus is directly bonded to benzene, which is a very good leaving group. Can be replaced by any group of your choice. Cl minus has no role to play in this case because Cl minus is not bonded directly to benzene. It just present to neutralize the charge on the nitrogen. This is BDC, and starting with BDC, I can prepare all four halobenzenes. For example, if you want to prepare chloro and bromo, we react the benzene diazonium chloride with Cu2X2, right, where X can be chlorine and bromine, and it forms halobenzene, bromo or chloro, and liberates colorless, odorless nitrogen gas. Now, this method of preparation of chloro and bromobenzene from the BDC using copper halides is called a Sandmeyer reaction. This is called Sandmeyer reaction. But we can also prepare chloro and bromobenzene from the benzene diazonium chloride using a copper powder in HX. Again, X can be chlorine and bromine. So the answer is again the same, halobenzene, chloro and bromo with the liberation of a nitrogen gas. But now this reaction is called a Gattermann reaction. Gattermann reaction. Now, iodobenzene can also be obtained by reacting this with a Ki. It decomposes to give iodobenzene, liberates colorless, odorless nitrogen gas, and the side product is KCl. Now, if you want to prepare fluoro, we react the benzene diazonium chloride first with HBF4, which is called fluoroboric acid. It gives another diazonium salt, which is bulkier than the first one. Since this diazonium salt is more bulkier, unstable, and decompose on heating to give a fluorobenzene. And the side products are BF3 and the nitrogen gas. Now, this reaction is known as Bose-Schiemann reaction. Bose-Schiemann reaction. In fact, this is the only method as far as your syllabus is concerned to prepare fluorobenzene or to add fluorine on the benzene ring. Now, next is how do you prepare a diazonium salt? Now, diazonium salt can be obtained, BDC can be formed from aniline. Aniline means you have a NH2 group directly bonded to benzene. That is a requirement. That NH2 group should be directly bonded to benzene. If you have a NH2 but on the side chain, you won't get diazonium salt. If you don't have a NH2 group, again you won't get diazonium salt. So only requirement is NH2 group should be directly bonded to the benzene ring. This is called aniline. This is called phenylamine. So we are reacting this compound aniline with NaNO2 sodium nitrite and hydrochloric acid in ice cold solution 0 to 4 degrees Celsius. But if you don't remember the temperature, you write ice cold solution. And it gives a diazonium salt. And the side products are NaCl and water. Now, this preparation of a diazonium salt from aniline is known as diazotization. This is called diazotization. So via diazotization, I can change my aniline into any halobenzene, chlorobenzene, bromobenzene, iodobenzene, anything. So I'll do one conversion for you that convert aniline into iodobenzene. So this is our question, aniline into iodobenzene. Now since aniline is already given, so we change this into diazonium, we convert aniline first into diazonium salt using NaNO2 hydrochloric acid, 0 to 4 degrees Celsius. It gives a diazonium salt. And this on reaction with Ki gives iodobenzene. Now one more question. Question is write the structure of A and B. Now suppose you are given this. On reaction with the NaNO2 hydrochloric acid, 0 to 4 degrees Celsius, it gives A. On reaction with HBF4, gives B. Now question is what are the structures of A and B? So first step is diazotization. You change NH2 into a diazonium salt. So this is structure of A. This is structure of A. Now B is another diazonium salt in which the anionic part is BF4 negative. You won't get fluorobenzene because we are not heating in the second step. So the structure of B is this, N2 plus and BF4 minus. So you read the conditions very carefully whether we are heating the diazonium salt or we are not heating the diazonium salt. Now the third method to prepare chlorobenzene is from benzene again. Reacting the benzene with hydrochloric acid in the presence of oxygen and CuCl2 is used as a catalyst. It gives chlorobenzene plus water. Now this reaction is called a Rastrick process. In this case, the oxygen first oxidizes HCl to Cl plus, and then Cl plus, once the electrophile is produced, attacks on the benzene ring to give a chlorobenzene. And the role of the copper chloride is to remove water from the right hand side and helps in shifting the equilibrium in the forward direction. So CuCl2 helps in the removal of water from the right hand side, from the RHS, and shift the equilibrium in the forward direction. So without electrophile, benzene H cannot be replaced. Equilibrium in the forward direction. So these are the methods of preparation of halobenzene. Now we will discuss about the properties of halobenzene, and the first one is in the properties of halobenzene. And whenever you have to take some halogen, you always take either chlorine or bromine. Now first is that halobenzene have a higher boiling point than benzene. This is one point. Second point is that halobenzene are immiscible in water. Because they are not capable of forming hydrogen bonds with water due to the presence of bulky benzene ring. Then third point is that halobenzene is less reactive than haloalkane towards nucleophilic substitution reactions. Means it's difficult to replace the halogen from the halobenzene than halogen from the haloalkane. For example, if you are reacting the chloroalkane with a dilute NaOH aqueous alkali, the chlorine can easily be replaced to give alcohol. This is called hydrolysis. But when we react the chlorobenzene with the dilute NaOH, nothing happens. So it means that chlorobenzene is difficult to hydrolyze. It means chlorobenzene is less reactive than chloroalkane. It can be any alkane. It means a CCl bond is more difficult to break than CCl bond in chloroalkane. than in chloroalkane. Now, if you look at the chlorobenzene, chlorine is directly bonded to benzene, and chlorine has 3 lone pair of electrons present. And this lone pair of electron can participate into resonance with the benzene. And remember, whenever the atom directly bonded to benzene has a lone pair, then the lone pair moves towards benzene, away from the group. This is called a plus resonance effect. Because the presence of chlorine has increased the resonance, but the electrons are moving away from chlorine, that's why plus resonance effect. Now these are the resonating structures, and when you draw the resonating structure, you have to show the correct position of the negative and positive charges and using the curved arrow notations. So this is second resonating structure. And this is the fourth resonating structure. And this is the last one. So you should know how to draw the resonating structures. Now, since lone pair of electron on chlorine participates into resonance with the benzene ring, with the benzene ring, CCl bond acquires a partial double bond character. As a result, bond dissociation energy increases. Therefore, the first point, more difficult to break CCl bond in chlorobenzene, more difficult to break CCl bond in chlorobenzene. It means more difficult to hydrolyze chlorobenzene by NaOH. It means chlorobenzene is less reactive towards nucleophilic substitution reactions. So this is one reason by which you can explain the 3 questions. Why it's difficult to break CCl bond, why it's difficult to hydrolyze chlorobenzene, why is chlorobenzene less reactive in nucleophilic substitution reactions. Now second reason, first was a resonance, second reason. Now if you look at the chlorobenzene, this is my alpha carbon. And this alpha carbon is sp2 hybridized, has a 33% S character. But the alpha carbon in chloroalkane, this is alpha carbon, this is sp3 hybridized, has 25% S character. And more the S character, more the electronegativity of carbon. More electron density on carbon. And since carbon has already more electron density, so more difficult for nucleophile to attack. So therefore, more difficult for nucleophile to attack at sp2 carbon than at sp3, and hence chlorobenzene is less reactive than chloroalkanes towards nucleophilic substitution reactions. And the third reason is that the phenyl carbocation means the carbocation obtained after the loss of Cl. Phenyl carbocation, this is called phenyl carbocation, is less stable than the alkyl carbocation are positive. So if you have to write only one reason, you write the first one, that is based on resonance. If you have to write the two reasons, you write the first two, or if you have to write three reasons, write all three. So it's difficult to replace the halogen of halobenzene. So we use drastic condition. So if you look at the nucleophilic substitution reactions, this is my chlorobenzene. So if I react this compound with just dilute NaOH, nothing happens, no product. So if you react the chlorobenzene with a dilute NaOH, then nothing happens, no product. But still, if you want now, I have to replace the chlorine by an OH, you have to use the drastic conditions. For example, we are reacting this compound with a dilute NaOH, 623 Kelvin, 300 atmospheric pressure, and use of all these drastic conditions also indicates that chlorobenzene is less reactive than chloroalkane. So it gives a phenol, but phenols are acidic in nature. They immediately gets neutralized by NaOH to give a sodium salt. So see how difficult it is to replace chlorine by OH. So it gives a sodium salt. This on acidification gives a phenol. You can write directly also, changing chlorobenzene into phenol, writing this way: dilute NaOH, 623 Kelvin, 300 atmospheric pressure, followed by acidification, it gives phenol. And once upon a time, this was a commercial method to prepare phenol called Dow's process. Dow's process. Now, second example of nucleophilic substitution is reacting chlorobenzene with ammonia. Ammonia is also nucleophile, but using just ammonia does not give any product. So again, we have to increase the temperature, use catalyst to increase the speed of reaction. So we use 475 Kelvin temperature. In the presence of Cu2O as a catalyst, it gives aniline. And the reaction is important because once the aniline is formed, I can change aniline into any other halogen compound via diazonium salt. For example, this is the conversion given. Convert chlorobenzene into iodobenzene. Chlorobenzene into iodobenzene. So this is the conversion. These are the steps involved. So we convert chlorobenzene first into aniline using ammonium, 475 Kelvin temperature, Cu2O it gives aniline. Then via diazonium, so I'm combining two steps into one using NaNO2, hydrochloric acid in ice cold solution followed by reaction with Ki. It gives iodobenzene. But many students they write chlorobenzene into iodobenzene using sodium iodide in dry acetone. There's a Finkel stain. But remember, Finkel stain is given only by haloalkanes, not halobenzene. Now, next reaction is a nucleophilic substitution, reacting chlorobenzene with a sodium cyanide or potassium cyanide. So I'm using sodium cyanide, but again nothing happens. So we use CuCN as a catalyst at 475 Kelvin temperature. It gives a cyanobenzene. This is called cyanobenzene. Has another name called a benzonitrile. And via this method, I can increase the carbon on the benzene ring. And once this CN is obtained, it gives all the reactions of the cyano group as we discussed in the haloalkane in the form of a flow chart. So the next thing is how can we increase the reactivity of the chlorobenzene towards nucleophilic substitution? See, nucleophile is electron rich atom or group. Nucleophile attacks at the electron deficient carbon. Electron deficient carbon means the carbon with less electron density. So if we are able to decrease, so if we are able to decrease electron density at alpha carbon, we can enhance the reactivity towards nucleophilic substitution. And the electron density at alpha carbon can be decreased. The electron density at alpha carbon can be decreased by using some electron withdrawing group. By using some electron withdrawing group, and very common example is the nitro group. So the presence of nitro group on benzene will enhance the reactivity towards nucleophilic substitution. Reactivity towards nucleophilic substitution using -I -R effect. For example, this is chlorobenzene and we are reacting it with the dilute NaOH. We are reacting it with the dilute NaOH. 623 Kelvin, 300 atmospheric pressure, and followed by acidification, it gives us phenol. Now, when the nitro group comes at the para position, then the reactivity increases and we use less drastic conditions now. It's a dilute NaOH and 485 Kelvin followed by H plus ion gives para nitro phenol. And if we have one more nitro group, the reactivity further increases. Now we have two nitro groups at ortho and para. Now the reactivity further increases, temperature further decreases. So now the temperature is 385 Kelvin followed by H plus ion. It gives us 2,4 dinitrophenol. We can simply write dilute NaOH. Now if we have 3 nitro groups present, if we have 3 nitro now present, now the reactivity is so high that this can be hydrolyzed even by the moisture in the air. It can be hydrolyzed even by the moisture in the air. The reactivity is so high now in this case. So this is the product form, and this product is called a picric acid. So main point is that the presence of a withdrawing group enhance the reactivity. And one more point you should remember, note down, that nitro group has a minus I effect. Nitro group has a minus I effect from all three positions, from ortho, meta and para. But minus R participates into resonance by withdrawing effect only from ortho and para. You should remember this because we use the same point again and again in different chapters of organic chemistry. Minus R only from ortho and para. This you should remember. Now the next category of reaction of chlorobenzene or halobenzene in general are the electrophilic substitution. Electrophilic substitution reactions. So now we replace the H of the chlorobenzene, H of the benzene in chlorobenzene without disturbing the chlorine. Now what is electrophile? Now electrophile is electron deficient, attacks at the electron rich carbon. Rich carbon means a carbon with more electron density. Now if you look at the resonating structures of chlorobenzene, the presence of chlorine increases the electron density at ortho and para position due to plus R effect. So therefore directs the incoming electrophile only at ortho and para but not at meta, because meta does not have any negative charge. But also this another is a unique group. Halogen is a very unique group. It's the orthopara directing, but at the same time it deactivates. But due to high electronegativity of chlorine, high electronegativity and large size of chlorine, lone pair of chlorine does not participate effectively in resonance with benzene. So chlorine is orthopara directing due to plus R effect, and chlorine is deactivating due to minus I effect. Now these are some examples of electrophilic substitution. And the first one is this. This is called halogenation of chlorobenzene. Now we will not disturb this chlorine. We are adding the second chlorine now, again in the presence of FeCl3 as a catalyst. This is called chlorination of chlorobenzene. So it gives us two products. One is ortho, one is para. So this is called orthodichlorobenzene. And this one is called para-dichlorobenzene. Para-dichlorobenzene. And since para-dichlorobenzene is more symmetrical, net dipole moment is 0, more tightly fit into the crystal lattice, crystal lattice in the solid state, and hence has a higher melting point than the ortho isomer. Higher melting point than ortho dichlorobenzene. So melting point is higher for the para isomer, but orthodichlorobenzene has a higher boiling point. Now more electrophilic substitution reactions of chlorobenzene. Now this is chlorobenzene. Now we are reacting it with the HNO3 and H2SO4. This is called nitration of chlorobenzene. Nitration. So it gives two products. One is orthoisomer and second is called para-isomer. This has a IUPAC name 1-chloro 4-nitrobenzene. Now second example is sulfonation of chlorobenzene. Sulfonation using a concentrated sulfuric acid. Again the two isomers are formed. I am writing name only for one. Second you can write yourself. This is a para-isomer. Now para-isomer has a name called 4-chloro benzene sulfonic acid. Next is a Fittig-Kraft alkylation using CH3Cl in the presence of anhydrous AlCl3. Now the methyl group comes at ortho and para. Ortho and para. This reaction is called Fittig-Kraft alkylation. I can use any alkyl group, and the IUPAC name of this isomer is 1-chloro 4-methyl benzene. And next is Fittig-Kraft acetylation using CH3COCl in the presence of anhydrous AlCl3. Now acetylation means this is very, very important. Acetylation means replacement of hydrogen by COCH3 group. When we replace H of the benzene, then the reaction is called a Friedel-Crafts acetylation. So this is Friedel-Crafts acetylation. So these are the two isomers formed. This is one, and this is a para isomer. And the ortho isomer is named as now as a 2-chloroacetophenone. This is a ketone functional group, and this compound is called acetophenone. So these are some examples of electrophilic substitution reactions of chlorobenzene. Now the third category of reaction is the reaction with the metals. Reaction with metals. And the first one is with sodium. With sodium metal. As you know, when haloalkanes reacts with sodium in the presence of dry ether, they form alkanes, RR. Now this reaction is called, they form alkanes, and this reaction is called Wurtz reaction. So Wurtz reaction is given only by chloroalkane, haloalkanes. Similarly, when we react the chlorobenzene or any other halobenzene with sodium in the presence of dry ether, again you have to form a new bond between the alpha carbon atoms, and this compound is called a diphenyl phenylbenzene, and this reaction is called a Fittig reaction. So in Fittig reaction we take aryl halides, and in Wurtz reaction we take alkyl halides. Now if we take one molecule of aryl halide and one molecule of alkyl chloride in the presence of sodium and dry ether, now you have to again form a bond between the alpha carbon atoms, and it gives you alkyl benzene. Now this reaction is now called a Wurtz-Fittig reaction. Wurtz-Fittig reaction. Now we'll discuss one example in the form of a question. Now suppose you are given, this is called chlorobenzene. On reaction with CH3Cl in the presence of a sodium, it forms A. A on reaction with chlorine in the presence of light gives B. B on reaction with sodium, dry ether, gives C. Now the question is, what are the structures of A, B and C? What are the structures of A, B and C? Now the first example is an example of a Wurtz-Fittig reaction. So the new bond is formed between the alpha carbon of chlorobenzene and the alpha carbon of chloroalkane. So this is called toluene. This is called methylbenzene. Now in the second step, we are using chlorine in the presence of light. So we'll displace the H of the saturated carbon by chlorine to form a benzyl chloride. This is called benzyl chloride. And in the formation of C from B, again this is an example of a Wurtz reaction, and the structure of compound C is this, involving a formation of a new bond between the alpha carbon atoms. It is called dibenzyl. Dibenzyl. This is the reaction with the halobenzene with sodium metal. Now second is a reaction with magnesium. Now, with magnesium, halobenzene also forms a Grignard's reagent where X can be chlorine, bromine, iodine. With magnesium, again in the presence of dry ether, anhydrous conditions, otherwise the moisture will decompose the Grignard's reagent to a hydrocarbon. So this is Grignard's reagent. So we'll take one question again. The question is, how do you convert benzene into deuterobenzene? Mean how to add deuterium on the benzene ring? Deuterobenzene. So first step is we perform the halogenation using bromine. In the presence of FeBr3, it forms bromobenzene. Then reacting it with magnesium to form a Grignard's reagent. In the presence of a dry ether. And in the third step, we use heavy water, and heavy water will decompose the Grignard's reagent to a hydrocarbon. Now, heavy water will replace MgBr by D. This is called a deuterobenzene. And the starting compound was benzene. So these are the reactions of haloarenes with metals. About the polyhalogen compounds. Important polyhalogen compounds. Polyhalogen compounds means the compounds containing two or more than two halogens. More than two halogens. For example, we have a CH2Cl2, we have CH2ClF, we can have CHCl3, we can have CCl4. So these are some examples of polyhalogen compounds. Now the first one is CH2Cl2. This is called dichloromethane. And used as a solvent and the second one is these compounds are called chlorofluorocarbons. And they are used as a refrigerant. So the most important polyhalogen compounds are polyhalogen compounds are the halo form. CHX3 called trihalomethane. For example, this is called chloroform. This is called bromoform. And this is called iodoform. Chloroform has a IUPAC name, trichloromethane. And this is tribromomethane. And this is called triiodomethane. Now, out of these three, chloroform and the bromoform are colorless liquids, whereas iodoform is a yellow solid, is a yellow powder. Now, all three haloforms can be prepared. All three haloforms can be prepared by compounds containing this group CH3CHOH, and remember this fourth valency has to be satisfied by hydrogen, by some alkyl group or some benzene ring. No electronegative atom should be present containing this group, or CH3CO. Again, the fourth valency has to be satisfied by H, R, or AR containing this group. So compounds containing either this group or this group can be used as a starting compound to prepare haloform. So we are reacting this with a halogen in the presence of an alkali, NaOH or KOH, and warm. Now, if you label these two carbons as A and B, then carbon A form a haloform and carbon B gets oxidized to form acid. But since our medium is alkaline basic, so that acid immediately gets neutralized to form a salt. So this is B. So carbon A gets oxidized to form haloform and carbon B gives a sodium salt of a carboxylic acid. This reaction is known as a haloform reaction. Very, very important reaction in organic chemistry. Haloform reaction. For example, this. Now this is given ethyl alcohol. So I'm writing the ethyl alcohol in this form. So it contains this group. It can be used as a starting compound to prepare a chloroform. So I'm reacting this with a chlorine, NaOH, and warm. So it gives me chloroform and the sodium salt of a formic acid. Similarly, this compound can be used. This is called acetone, propanone. It also contains this group, and on reaction with iodine, NaOH, and warm, it gives me a yellow precipitate of iodoform, which can easily be detected. And the side product is a sodium salt of a acetic acid. But if you are starting with the acetic acid and you are reacting it with iodine and NaOH, then you won't get any yellow PPT of iodoform. No yellow precipitate of iodoform, although in this case CH3CO group is present, but fourth valency has been satisfied by oxygen electronegative element, so it does not give haloform reaction. Does not give a haloform reaction. Next point, this chloroform is a colorless, a sweet smelling liquid. Sweet smelling liquid, and on reaction with oxygen, air, chloroform forms or chloroform gives a poisonous phosgene gas, COCl2, chloroform on reaction with air, oxygen, in the presence of light, it gives COCl2 plus the HCl. This is called phosgene gas, poisonous. And due to this reason, chloroform is stored in dark colored bottles. So this is our reasoning question. Dark colored bottles containing a small amount of ethyl alcohol. Small amount of ethyl alcohol, C2H5OH. Now the role of C2H5OH is to convert phosgene, if any form, into a non-poisonous diethyl carbonate. So this is the equation, COCl2 plus twice of C2H5OH. It gives a diethyl carbonate plus the twice of SC. Now next is this chloroform. On hydrolysis gives a salt of formic acid. For example, this is chloroform. We are hydrolyzing this with aqueous KOH. All three chlorines will be replaced, but more than one OH at the same carbon is unstable. It results in the loss of water to give a formic acid, but since our medium is alkaline, immediately gets neutralized to form a salt. So this is our final product, potassium salt of a formic acid. Next is this chloroform on reaction with primary amines. On reaction with primary amines means the compounds containing NH2 group. Any compound containing NH2 group is called primary amine. And alcoholic potash, ethanolic potash, KOH, alcoholic potash, KOH gives a product with very unpleasant smell. Of isocyanide. This reaction is known as a carbylamine reaction. Or isocyanide test. And this is the equation involved. This is chloroform on reaction with any primary amine, aliphatic, aromatic. The only requirement is NH2 group should be present. and alcoholic potash, warm. It gives a product with very unpleasant smell. So NH2 group has been converted into NC. This is called a carboylamine. This is called isocyanide. Unpleasant smell, foul smell, obnoxious smell. And these are the side products, KCl plus water. Now this chloroform is used as a solvent. Used as a solvent in paints, polish, and iodoform used as an antiseptic. And antiseptic properties are due to the liberation of iodine. Not due to iodoform, due to the liberation of iodine. Now one question we'll discuss now. The question is what happens when aniline is being treated with a chloroform and alcoholic potash. So in these type of questions, we have to write the equation. So my equation is this. This is aniline is being treated with chloroform. This is isocyanide test and alcoholic potash. Warm. It gives us phenyl isocyanide, KCl plus water. This product is called phenyl isocyanide, and this is called aniline. Now next is carbon tetrachloride. CCl4 is also mainly used as a solvent. Organic solvent, and also used in fire extinguishers. Now one more polyhalogen compound is called a DDT. Now what DDT stands for? It stands for diphenyl dichlorodiphenyl and trichloroethane. And this DDT is obtained by reacting this compound called a chloral. This is called trichloroethanol with chlorobenzene. This is chlorobenzene. Two molecules of chlorobenzene in the presence of concentrated sulfuric acid. This is a loss of water. Dehydration takes place and it gives us a DDT. So this is structure of DDT. And DDT is used as a pesticide. But it causes water pollution. And DDT on reaction with hot and alcoholic KOH, this is DDT, undergo loss of HCl, dehydrohalogenation, hot and alcoholic KOH, undergo loss of HCl to form CCl2 double bond C, which is biodegradable. Although DDT is not biodegradable, but this product is biodegradable.